So shall we start?
Yeah, sure, ma'am.
2 minutes more.
How many participants have joined?
79. So shall we start?
Yeah, sure. How many participants have joined?
79, sir. Two minutes. We'll wait for 2 minutes, sir.
Okay, madam, no problem.
Okay, sir. We'll start.
Okay, ma'am.
Good morning to one and all. Welcome to third day of online FDP on machine learning and deep learning. I welcome you, sir, and all the participants for today's session. For the remaining 3 days, the session may exceed up to 30 minutes. Kindly cooperate. A few instructions to the participants. While you're submitting the assignment, attach a Word or PDF file because some participants have attached an image file and a screenshot. Please avoid such attachment. And many participants are asking how to interact with Sir. So I told you many times to ping me in WhatsApp so that I can connect you with Sir. I will give you the StreamYard link to the person who wants to interact with Sir during the session. And the feedback link will be given on the last day of the FDP. That is on 31st May. So now I hand over the session to Jude, sir. Sir, please take over the session.
Okay. Welcome, participants. Thank you for attending the workshop for the past 2 days. And today is a brand fresh day, and we are going to learn something new in this day also. Right. So, just to give a summary of what we have learned so far, we have seen the technical aspects of artificial neural networks in the last class, right? And we have discussed some training algorithms also. We discussed about the backpropagation neural network, the architecture, how you have to design your algorithm, these two aspects. Once again, I want to reassure that the thing which we left in the last session, self-organizing map, that I will be dealing it today. So with this background of the idea of how an artificial neural network works, now in this day, we are going to see the application part of the artificial neural networks. So the title I have given is Unconventional Soft Computing Techniques for Medical Image Analysis. The application I have chosen is medical image analysis. I hope most of you may be working in image processing. And the first word is very, very important, unconventional. When I say unconventional, it is something not usual, right? When everybody goes in the conventional BPN algorithm, what we are going to do is we are going to think creatively, think out of the box, and create some modified approaches, which will be better than the conventional approach. So this day, the agenda will be the application case study, we'll be seeing everything as a whole, not one by one. Everything is inbuilt within the other. Application or case study, when we say case study, it is not somebody else's case study, it is my own research works, which I'm going to present here. And the practical implementation concepts, how to design a neural network before going for practical implementation. And then the creative approaches. I'll be showing two creative approaches. If you refer Google for my publications, you can find n number of approaches. But because of want of time, I am sticking on to one supervised and one unsupervised model creative approaches. It will be something different from the conventional method. And then I am interested to show code for one of these things. I hope I will finish everything within the stipulated time. And then we will have the, as usual, question answer session. So now we'll go into the part medical image analysis, right? Image processing is very much useful for many applications, right? With the images, we can take plenty of
Sir,
information.
sir, sorry to
Yes, ma'am.
interrupt. Your video is not visible, sir. PPT is
Just
visible, but your video.
should I reconnect again, ma'am?
Okay, sir.
Is my video visible now?
No, sir. PPT is visible, but your face is not visible.
Shall I close and reconnect again?
Okay, sir.
Madam,
Okay,
your
sir.
not
Sir?
visible. Your video is not visible. So is it that okay?
Okay, no problem, sir. Put your PPT.
Okay, I'm sharing it again.
Is it okay, sir? Now it's fine.
Now it's fine.
Yes, sir. And you hide that screen also on hide sharing.
Is it okay?
Okay, sir.
Okay, now we'll go into the concept of medical image analysis. And image processing, as I told you, is useful for many applications, especially the concept of medical imaging, right? The doctors will assess the abnormalities of a human being with the help of images. Nowadays, wherever you go, immediately they ask you to take a scan, right? With the help of the scan, they are going to assess or diagnose how far you are affected by the specific disease. In our application or case study, we have taken the concept of brain tumor image analysis. That means when a patient is suffering from a headache or something of that sort, he will be asked to take a scan. And the first thing the doctor will do is he will identify what type of the tumor the patient is suffering from. Because in brain tumor itself, we have so many types, right? That is the main application of brain tumor image processing methods. Right? Now we will see how our artificial neural network can be used or incorporated in that so that a better decision making skill can be taken by the skill is available to the doctor. Early and accurate identification of brain abnormality is highly essential, right? So it is a life or death problem. So the two things are very, very mandatory. The first thing is the accuracy, how far you diagnose the disease accurately. The second thing is how quickly you diagnose, right? You cannot ask the patient to take a scan and come and get the results the next day. Normally, conventional method, it takes some hours, 2 hours or 3 hours. But how far quickly you can take and how far you can detect in the early stage, these are some of the concepts which has to be supported by the artificial system which we develop, right? Remember, these are the system which is only to assist the doctors. We are not going to replace the doctors. It is going to assist the doctors so that they can take a better decision. So abnormal chagnification includes two major processes, right? These are the two things which you have to always keep in mind. Image classification is different from image segmentation. These two things go hand by hand, but they have a difference in them. When we say classification, you take an image and identify which abnormal category this image belongs to. That means the data which you require for image classification is huge. You need at least 100 images, say for example, from 4 classes, and then you identify whether each image belongs to class A or B or C or so you are processing the image as a whole. But when you go for image segmentation, it is processing within the image, right? Say for example, you see my face, right? If you diagnose my face as Jude, then that is called as image classification. If you say that my ears are like this, my eyes are like this, that means within the face, if you take some conclusion or some partition or some clustering, then we call it as image segmentation. So, what is the purpose of this image segmentation? When a patient is diagnosed with a specific tumor, he will be receiving some treatment, right? But we do not know whether this treatment is going to have a positive effect or a negative effect in the human being. So after a few days, again, we will be taking a scan and we will check whether the tumor portion shrinks or expands. So that shrinkage or expansion of tumor pixels in the image can be determined by segmentation. So first you have to go for classification. After categorizing, you will go for segmentation. So image classification is used to identify the type of the disease. It is completely an image-based operation. Image segmentation corresponds to detecting the volume of abnormalities. How many tumor pixels are available? When I say pixel, pixel stands for picture element. A small box. You would have seen an image in a computer where if you zoom it, you will see small, small boxes, right? Each box corresponds to a pixel or a picture element, which will have a numerical value within it. Based on that, if you go for segmentation, if you go for processing, then we call it as segmentation. Accurate identification is important. Wrong identification will lead to fatal results because you cannot take a chance in the life of a patient. And again, these abnormalities are normally taken. Conventionally, what happens? Taken by a doctor who is highly prone to error. Psychovisual effect, right? That is the thing because human perception differs. If I say this background of my PowerPoint is good, somebody say it would have been better, right? So when you go for human perception, that it will always change. But when we miss each or every or even a single pixel, it is going to be dangerous for the human being. So we need a system which is completely unbiased towards the process. For that, we go for a automated system. Besides being inaccurate, this method also consumes large time period. They will be asked to take many tests, then scan, you have to wait. Everything is there, right? So why don't we have an automated system which can improve the accuracy and reduce the convergence time? That is the main objective of using ANN for medical image analysis. So we can say that many approaches are available, but artificial neural networks, as we saw in the previous sessions, it is going to be sufficiently good for any practical applications. But still, there is scope for improvement. That's why we say modified artificial neural networks need to be developed, which can ensure high accuracy with quick convergence. So, in this session, what I'm going to teach you is we are going to take image classification and image segmentation. One model for image classification and one model for image segmentation. The model I have chosen for image classification is BPN, which we have seen already in the previous session. And for image segmentation, we'll be going for BPN. For image classification, we'll be going for a self-organizing map classifier, which I missed in the previous session that I'll be dealing in this session. Along with that, we are also going for two modified approaches. One is modified BPN and the other one is modified SOM. So this is the proposed research flow, right? If you are into uh, MRI image analysis or brain image analysis, you can very well take this flow chart and work on. If you are beginner, if you are interested in image processing, or if you're planning to do your project, you can take this sketch, right? So the first step of your image processing is collection of database. The second step is all the images by default will have some noises, right? How to remove that noise. That is the second step. And the third step is called as feature extraction. In the previous session, I told you that whatever may be the image, analog data, when it goes to the computer-based system or artificial neural networks, it will be converted into numbers. One method of converting your images into numbers is called as feature extraction. We have other specifications also that I will explain later. For the time being, you understand like this. Then we go for your image classification on your left-hand side and image segmentation on your right-hand side. We see two networks for classification. We see two networks for segmentation. Then we'll go for a performance analysis and we can. So these are the different research modules. First one is we are going to see about the image database and image pre-processing. MRI, if you are working in brain images, I would suggest you to go for MRI images, right? There is also another advanced one called as fMRI. I'm not sure how many data will be available in India because it is quite expensive. So if you are able to get some MRI images, you can very well work on this because this MRI captures the brain very accurately so that the decision making by the neural network will be much more better. And this collection of MR brain images can be done with the help of two types of data collection is there. One is called as the real-time images, where you need to approach some doctors and you need to collect the data. And the other one is you can collect the images from internet. I will tell you the both the ways. And the images which I have used here are collected from Devaki Scan Center from Madurai. You can either approach a radiologist. When we say radiologist, he is a person who is in charge of a scan center or something like that. Even big hospitals have some radiologists. And some images are collected from KG hospitals, Coimbatore. These images belongs to four categories: meningioma, astrocytoma, glioma, and metastasis. After getting output from a neural network, I will again approach the doctors for their validation. So always remember, when you have your input data, the ground truth is also very, very important. What do you mean by ground truth? The decision taken by doctors. They will draw in the image the portion of tumor and they will give you. When you get an output from artificial neural network, you can compare these two things and you can check how much success your approach is. And these are the type of images. So as I think I remember one question asked, how many images we need to collect, right? Triple digit, 3 digit is compulsory when you go for research. More the number of images, the better will be your accuracy. And these real-time images are used for image classification and you can also use for image segmentation. And these are sample MR images. If I do not show you the name, you will not be able to identify which image belongs to which category. Right? Because everything seems to be white. The white portion corresponds to the tumor of that specific patient. So when everything looks same, right, there's a chance that human being may take, I will not say they will take, they may take a wrong decision at some point of time. To avoid that, we have this automated system. And all these images are not color images. Even though if you have a color image for processing, you can convert to gray level image with a dimension of 256 cross 256. And some images are having a bigger dimension depending upon the MR machine, which is going to scan the portion of the body or the brain. If you are unable to collect the images from the doctors, there are also many images available in the websites. Many Canadian universities, American universities. One example is the link I have given here from where you can take some data. I am not sure this has taken long back, but still I feel that you can find the data here. And these images I have used only for segmentation. The reason is they have not given the specific classes of that images. If I do not know the specific classes of the images in advance, I cannot train my neural network. So I have used for segmentation because they have given the ground truth or the expected output of the internal parts of the image. There are four internal parts of brain image. One is called as white matter, gray matter, CSF or cerebrospinal fluid, and the tumor portion. The fourth portion is important for. So these are the images, right, available in the website. And if I do not show you the name as mild stage, moderate stage, and severe stage, even I feel very difficult to see where the tumor portion is, right? Even in such cases, your network should be able to uh, classify or identify the abnormality. So when you go for segmentation, as I told you, you are going to process within an image. So your training data and testing data will be in terms of pixels, right? 40 pixels. A portion of an image corresponds to 40 pixels. Another portion of an image corresponds to another 40 pixels. Because the tumor portion is very less, I could get only 20 pixels of training data. But when I go for testing, I'm going to use the entire image. Even though I told you training and testing should have a different data, 20 and 40 will not make much impact on that. So this is the next step, a pre-processing step, how we can remove the noises from the MR images. Right? If you look at these images, the first column corresponds to the input images. Can you see an outer ring covering that border of that image? Right? That corresponds to the skull portion of a human being. So whenever a patient is allowed to enter into an MRI scan, the scan will take few portion or bits of skull along with the brain tissues. But the beauty is the skull will also act as a tumor tissue when you go for assessments, which is not actually the tumor tissue. So what you have to do is first you have to remove the skull portion or the circular region of that images. So I have passed through series of steps. Column 2 corresponds to second stage, column 2 third stage, column 4 fourth stage, and when you look at the final image, you can see that the ring portion is removed. There are some traces of ring, but it is has been removed to major extent. Now we will see how we have removed it. This is based on a single image processing. This is not related to ML or DL. This is based on a simple image processing steps where we make use of morphological operations, gray to binary conversion, and specifically I make use of a concept called as mask. Right? When I place a Spider-Man mask in my face, we feel that we have become a Spider-Man. So what I have done is I have created a mask. This mask is nothing but the fourth image, right? I have created a mask from the original images and I have multiplied column number 1 and column number 4. So white corresponds to 1 and black corresponds to 0. So whatever is multiplied with white, that portion alone will come in the output. You understood? Whatever is multiplied with black, that portion will be removed. So I have gone through dilation and erosion. It's like smoothing an image, right? When we smoothen the image, the portion of the skull becomes, or the intensity becomes low. When it becomes low, automatically it disappears from your original image from where you can make a mask. Once you create a mask, you put it or overlap it on your original image from where you can get a skull-free images. When you look at the last column, this is how I analyze my output. I have got something of efficiency in the range of 98. That means still some traces are left out. Right? Still some traces are left out. And the average time period is very, very less because I want to make some quick systems. I need to consider all the time period of all the processes. Now we'll go into the concept of feature extraction. Right? After removing the unwanted noises or the skull portion of that image, I come into the process of feature extraction. These are the method which capture specific important information from different categories of images. Metastasis is different from glioma. How do you identify? Not by seeing, but there are some information which is represented in terms of angular second moment, contrast, correlation. These are mathematical equations which are already available in Google. You can browse that and check. Variance, inverse difference movement, entropy, skewness, kurtosis. There are many other features, but I have chosen 8 features for my research work. Now, this is the result of feature extraction process. What do you see here? Many values. But if you look at the ASM of metastasis, it is different from ASM of meningioma. ASM of glioma is different from ASM of astrocytoma. Then you can say ASM is a good feature which is able to capture the important information from that specific images. Similarly, when you look at all the features, all are able to give some different values for each image categories. Similarly, you go for image segmentation. Now, the problem with image segmentation is how to have a feature extraction, because the formula says it is for the whole image. But when you go for a segmentation process, each pixel has to be considered. So when you consider in a pixel, you can take a 3 cross 3 window. That means you take a center pixel, and along with the center pixel, you can take 9 pixels, right? 3 cross 3. So that 9 pixels will be acting as an image. So for that 9 pixels, you are going to extract the features, right? Not only for the pixel which are of interest, but also to the neighboring pixels. Again, the same features gives very good differentiable values. So this is example for another type of synthetic images, or the images taken from the website. Now we go into our important part. That's why whenever you go for an application, immediately you cannot go and put into your artificial neural networks. You need to have some initial steps, right? In our case, we had pre-processing and feature extraction. But when we go for different applications, we will be having different concepts before going into the process of ANN based image processing. So here we are going to see about ANN based image classification, and the method I am going to use is self-organizing map, right? Self-organizing map is also called as coherent neural network. It is framed by the scientist called as coherent, so it is also called as coherent neural network. And I am also going to give you an out-of-box thinking approach, which is derived by me, which I'm going to call it as modified self-organizing map 1. I have MSOM 2, 3, 4, and many things, but I'm going to give you the simplest possible. So first, what you have to do, the image data set is divided into training images and testing images. And the ANN is trained with the features of the training images from the all the 4 categories. A specified training algorithm is used for these networks. And we go for testing. That's what I'm going to tell you today. We are going for testing to check what is the actual result of artificial neural network. And these results are analyzed in terms of classification accuracy, sensitivity, specificity, complexity, and convergence. And how do you analyze the success of your neural network? We have some performance measures, right? We call it as classification accuracy, sensitivity, specificity, computational complexity, and time. 4 and 5 corresponds to time. 1, 2, and 3 corresponds to the accuracy measure. And these accuracy measures are based on 4 variables, I would say, called as TP, TN, FP, and FN. True positive, true negative, FP, false positive, false negative. The second term, positive, negative, denotes the actual situation, right? If it is positive, yes, the patient is suffering from that disease. The first variables, true, true, false, false, denotes your approach result. So true positive means the patient is actually suffering from the disease, and your method is also correctly identified that patient is suffering from that specific disease. And among these 4, the dangerous is false positive. What do you mean by false positive? Positive means the patient is suffering from disease, but your method has failed to identify that the patient is suffering from that specific disease. So true means correct identification, false means wrong identification.
Sir, one second, sir.
Yes, ma'am.
The PPT, the font size is very small, I think. Participants are saying it is not clear, visible.
If I increase the font size, it may go beyond
Photo
the
like,
frame.
okay, sir.
Should I increase
Okay.
that?
No, sir. For tomorrow we'll see, sir. You can
Okay.
proceed, sir.
Okay. So whenever you go for implementation with medical image analysis, you need to also give the specifications of your computer, right? That is very, very important when you go for writing a research paper, what software you have used, what is the RAM capacity of your processor. All these specifications should be given. Only then a person or a reviewer or an editor can identify how far your results can correlate with the computing capacity of the system. And now we go into the concept of self-organizing map, right? The last class, last session, I missed it. Now I'm going to teach you about the self-organizing map approach. It is a single layered ANN, right? What is a single layer ANN? You will have one input layer and one output layer, right? That is the concept of a single layer ANN. And when you have a single layer ANN, you can also see the process is relatively simple because you will have only one set of weights between input layer and output layer. Unlike BPN where we had two set of weight matrices. And importantly, this utilize unsupervised training methodology, right? That means if you do not have your pre-known data, then you can very well go for unsupervised training methodology. Even if you have, you can even check that whether how the system works, right? So remember, this is a single layer ANN and also a unsupervised approach. And the first point you have to remember is number of input layer neurons should be equal to number of inputs, right? Now my input is not an image, but the numbers which I have extracted from the image, which corresponds to 8. So I have 8 features in my input layer and 4 output layer neurons, which corresponds to 4 classes. Number of output layer neurons is equal to number of predefined classes. And the objective of training is to determine the stabilized weight matrices. Now we'll go into the training algorithm. Relatively simple. First step, what is step number 1? You need the input and you need the weights. You have your inputs, but you do not have the weights. They are usually randomly initialized. So in the second step, normally you will see that net value calculation takes place in most of the neural networks. That's what I said yesterday. But this SOM is slightly different, which depends upon the distance measure. Net value calculation is for BPN and distance measure is for self-organizing map, right? Net value calculation means multiplication, which output should be maximum. Distance measure means difference, where your output should be minimum. Right? So here I have two suffixes. What is I and J? I corresponds to the input layer neurons and J corresponds to the output layer neurons. I varies from 1 to 8 and J varies from 1 to 4. So now what I'm going to do is for each output layer neurons, how many neurons I have? 4. For each output layer neurons, I'm going to find the distance. So D of 1, D of 2, D of 3, D of 4. I will vary from 1 to 8. J will remain as 1 when I find D1. J will remain as 2 when I find D2. And I also will change. With this, you can find 4 distance value. Your W is random, your X is your input. After finding your distance value, you have to find out which neuron among the 4 is going to give you a minimum value. That you have to choose. Then you are going to update the winner neuron's weight. So what I'm going to say is, whichever neuron is going to give you the minimum value, he is going to be called as the winner. So that neuron's weight alone will be changed. Say, for example, if you say the 4th neuron is the winner, he is going to give you a minimum value. Then all the links with that arrow mark towards 4, right? From 1 you have, from 2 you have, 3 you have, 4 you have, till 8 you have. All these weights alone will be changed. So even though you have a weight matrix, you are not going to change all the weights. You are going to change only one column of that weight matrix. So this is the difference between BPN and SOM. BPN, you have net value. SOM, you have distance value. In BPN, all the weights will be adjusted, but in SOM, you are going to find the winner neuron, and only that weight will be adjusted. So what is the formula for this? Concept will be same. W new is equal to W old plus alpha into something new. What is alpha? Yes, alpha is the learning rate. And within that differential term, we have like xi minus wij old. Right? So if you know w old, if you know x, if you know alpha, this weight value can keep on changing. If the weight value changes, distance measure will change. If the distance measure changes, winner neuron will change. If the winner neuron change, again one column of weight will change. So all the columns of the weight matrix will get adjusted at one point of time, but one at a time. So now what you have to do, keep on proceeding like that. And in the BPN, I told you, you have to find the error value. Because what is the formula for error? Target minus output. Because you had target in BPN, it is possible. But in SOM, you do not have targets. So error calculation is not possible. So you have to depend only on the number of iterations. You repeat the approach for sufficient number of iterations, and then finally whatever weight value you are getting at the end of that specified iteration, that you are going to take as your correct value. Will it be correct? Nobody knows. Sometimes it may be correct, sometimes it may not be correct, because it is going to be unsupervised in nature, where accuracy is always very, very less. So these are the results I have got. Confusion matrix. So when I go for testing my network, I will give an unknown input and check at a single attack, right? Or other means there will not be any weight updation. In a single step, I will be able to find out whether this belongs to this category or not. I will have a predefined class, and I will say that 58 images of class 1 belongs to class 1 category. All the diagonal values corresponds to the correct matched class. Right? I know the predefined class, and when I give an input from unknown data, if it matches to that specific class, then that will be incremented or counted as 1. If you look at class 1, meningioma, 58 images have been correctly classified. 9 images of class 1 has been wrongly classified or misclassified or misunderstood as class 2. 8 images of class 1 has been wrongly associated with class 3, and 7 images of class 1 has been wrongly associated with class 4. Right? Similarly, when you go for class 2, again 52 images have been correctly identified. We have so many images in glioma. Among glioma, 52 images have been correctly classified, and remaining 9, 17, 24 images has been spread among the different classes. How will you find this? Based on your predefined output neurons. You have 4 neurons, you have a predefined class. Check which neuron is going to give you the minimum possible value. In BPN, it is maximum. In Cohonan, it is minimum. Next, from this, you are going to find out TP, TN, FP, FN value. What is TP? All the diagonal elements, correct classification corresponds to TP. What is TN? True negative. So for finding true negative, what you have to do is, if it is 58, you look at that number 58, leave that corresponding column and corresponding row, right? Leave that corresponding row and corresponding column. That means leave the first row and the first column. The remaining 3 cross 3 matrix values should be added, and that is taken as 196. These are all the negative images, but which has been identified as true. That means not class 1. Yes, I have identified correctly as not class 1. Right? So when you look at your false positive, again it corresponds to all the features which are in the column-wise arrangement. Say, for example, class 1. Class 1, you leave that 58 number correctly classification. Remaining 7 plus 7 plus 8 is 22. That comes to FP. And similarly, if you want to find for class 2, leave that 52 number. 7 plus 6, 13 plus 9 is 22. Likewise, you can find false positive. Column-wise addition, leaving the correct value is called as FP. When you go for FN, row-wise addition, leaving the correct value is called as F. Right? You can note it down if you want. Right? When you say TP, it is all the diagonal values. When you say TN, leave that full row and full column, add everything together and have for TN. When you go for FP, column-wise addition, leaving the correct diagonal terms. FN, it is the row-wise addition, leaving the correct diagonal terms. Then we have the formula, we can find the accuracy. Accuracy corresponds to 86% here, which is not sufficiently good for practical applications such as medical image analysis. So I have did a small computational operations also. So mathematical operation, when I look at my algorithm, I have only two equations. One is the equivalent distance calculation equation, and the other one is between the weight adjustment equation. If I say one subtraction and one multiplication for my first equation, then I say two mathematical operations. For A neurons and P output neurons, I will have 2 AP. Similarly, I will have 4 AP. When I put together, it will be 6 AP. So if you change the number of neurons in the input side, depending on that, the complexity will increase. And it has taken approximately around 650 CPU seconds. So this is based on the specification of the computer which I have used. So what do you infer from your self-organizing map classification? The first drawback. This is what a researcher has to do. Whenever you find or whenever you apply something, try to find or pinpoint the drawbacks. The first one is lack of standard convergence condition, right? BPN, we had error equation. Here we don't have any error equation, which is a drawback. Dependent on iterations. How many iterations you should use? Nobody knows. When you keep on iterating, sometimes you may cross the best result also. And single layer ANN. Single layer ANN always has the drawback of giving low accuracy, right? Perceptron. Yesterday I gave an assignment called as perceptron. If you would have read that perceptron, you will know that what is the drawback of a single layer artificial neural network. That's why we go for multi-layer, and now we end up with deep learning, which has huge number of layers. And the fourth one is accuracy will be affected if you are using unsupervised training algorithm. Though computationally effective, I will say this is quick, right? Comparatively to BPN, this is quick. But for my application, I cannot make a compromise on my accuracy. So how can I change that? So this is what a creative thinking comes into picture. You look at my previous algorithm. Yeah, this is our algorithm. And what is being done in step number 3? We are finding the distance, right? We are finding the distance for each neuron, and my expectation is the distance should be always minimum. What is the minimum possible value in mathematics? 0. So I want to make distance as 0, right? If I make distance as 0, then the possibility of convergence will be high. For achieving for that specific condition, I keep on changing my weights. I do not know what should be my weight. So I use an equation in step number 5, find a weight, and keep on checking that whether my D is minimum, D is minimum, D is minimum. But there is another way by which you can make D minimum. How can you make D minimum? Simple, right? If D wants to be minimum, D should be substituted with a value of 0. If D is equal to 0, then we can say Wij minus Xi is equal to 0. Then we can say that Wij minus X or X minus W is equal to 0. If X minus W is equal to 0, what do you mean by that? X is equal to W, right? Instead of going through a mathematical equation to find the value, if I straight away substitute X is equal to W, what I will get from that first equation? D is equal to X minus W. X minus W, when I substitute X is equal to W, it will automatically become 0. So I had this idea and thought, why don't we go for just assigning my inputs as weights for this expression for the testing process? That means there will not be any iterative calculation of weights. The weights will not be changed further and further. Why you change the weight further and further? Only to make the minimum distance or the distance to be equal to 0. But we have some practical issues in the implementation part. The first one is my features has a very huge number. But when you go for weight, it should be only between 0 and 1. So what happens here is I am going to normalize my data and bringing it into the range of 0 to 1. Once I bring my data x in the range of 0 to 1, I can very well assign it to my WR weights. Now, after assigning that, I will go for my testing process. What is testing process? Is same as that of my conventional SOM, but without any iteration. I just take my weights, substitute there, I will show that once. I will just go to step number 3. I have my weights already calculated, weight substituted there. I will find the distance, and whichever neuron is giving me a minimum distance, I will allot my specific input to that specific category, because I know predefined. First neuron is class metastasis, second one is so and so. So I can easily classify my data. That is called as testing, which is relatively easy in comparison with training. Training and testing are same. When you go for training, you will do the same process iteratively. When you go for testing, you are going to do the same process, but for only one step with an unknown input data. So what happens? The iteration dependent nature of SOM is eliminated. I don't want to depend on my iterations. So when you look at my results, you would have seen a better confusion matrix in comparison with my SOM, and my accuracy has improved to 95%. Right? When you write a research paper, you should not stop with this. Now tell me the reason why my accuracy is improved, or what reasons you think would have improved the accuracy of your MSOM1. The first one is because my iteration is eliminated, the weight matrices which I have is more converged weight matrix. It's not a random weight matrix, it is more converged weight matrix. Right? Again, when you go for iteration, there may be some rise, some fall. Sometimes error will increase, sometimes error will decrease. Even though you cannot calculate error, you can virtually have an error concept, right? It will increase or decrease. But when iteration is removed, my concept will keep on moving in a better way, or my convergence condition will be in a better way, that neural network will converge in an accurate way. Right? Ultimately, I can say the weight matrix which I achieved with the help of MSOM1 is better than the weight matrix which I achieved with the help of SOM. Also, the time is also significantly reduced. Even though time is not an issue, my accuracy is improved a lot. This is one way how you can have an out-of-box thinking. Right? For that, you need to have a deep understanding of the algorithm which you are explaining. So once you are good in SOM, you can find out why do we change it again and again, or what makes it computationally complex, or what makes it less accurate. Try to find out that reasons and find a solution to solve. Now we go into ANN-based segmentation. Why image segmentation in brain images? Taking the abnormal portion from any MR brain image. The explanation I gave you in the first slide. So I want to find out how many tumor pixels are available in the image even after the treatment has been carried out. So again, for this, I'm going to use two networks. One is our conventional BPN. I will not explain now, that we saw in the previous class. And now I'm going to tell you about modified BPN or backpropagation network. These networks are tested with both simulated images and real-time images. Why? I have the ground truth from the doctors for real-time images. I have the ground truth from the website also. But when I go for classification, I do not have the ground truth for simulated images. So I stopped with only the real-time image. So what are the performance measures for this? When you go for classification, we had accuracy, sensitivity, specificity, and so on. But when you go for segmentation, we have two important different measures, which we call it as segmentation efficiency and correspondence ratio. When you say segmentation efficiency, it shows how efficiently you have counted the number of tumor pixels within an image, or how efficiently you have segmented the number of tumor pixels within an image without missing any one of the pixel. But correspondence ratio shows how many extra pixels other than tumor pixels has entered your output. Right? Segmentation efficiency means not even one pixel should be missed out. Correspondence ratio means how much extra unwanted pixels has come in your output. So these are the two measures by which segmentation can be checked out. And as usual, we have the convergence rate. So this is general procedure for implementation. How we had for classification, we have a procedure for segmentation also. Divide into training data set and testing data set. Now, can you tell me how many images you have? How many images you need to process? Only one image. Segmentation means processing within an image. So it is sufficient to have only one image where you will have 65 536 pixels roughly, right? So 256 into 256 comes to 65 536. That you have to divide into training and testing. Choose some pixels from CSF, choose some pixels from gray matter, choose some pixels from other tumor portion, and finally you can have a training data set. If your tumor portion is very small, it is sufficient to take few training pixels. That's okay, right? All the other things can be used for testing. So ANN is trained with the training pixels. Same way, you need to convert that pixels into features. I told you the procedure for feature extraction using the 3x3 window method. Finally, the network is tested with the testing data. So this is what we saw in the previous session. I hope you remember, you have a good idea. 8 features, 4 output classes, number of neurons in the hidden layer, nobody knows, but I have kept it as 12. This algorithm we saw in the last session. So based on this algorithm, I am going to do the modification. That's why I'm showing you the same slide. So this is the results with the normal BPN, right? When I train my BPN and then when I test my BPN, when I say I'm testing my BPN, I'm going to check whether each of my pixel belongs to gray matter, white matter, CSF or tumor. If it is tumor, I will mark it as 1. I will take another pixel. Again, I will go to the same procedure. Again, third. Likewise, I'll complete for all 65 536 pixels and convert it into an image. All 1 will be converted, all 2 will be converted, all 3 will be converted, all 4 will be converted. We have a step for that in image processing, right? So if you look at the outputs, phantoms, right? Phantoms means the ground truth available in the website. If you look at an image, that image will be very good, very clean. The bottom FGHI corresponds to my results, right? Which I have used BPN and segmented gray matter, white matter, CSF, and tumor, right? Both will not be exactly same because segmentation is very, very difficult because you are playing with minute detail. Classification is relatively easy. This is for real-time images, right? So if you see that white portion, that tumor phantom is the third one. Doctor gave me the third column results and the second column results is my output. So I'm going to compare these two things and check if my white and doctor's white are same, then it is perfect. If not, how can I improve? And these are the values, segmentation efficiency and correspondence ratio. It comes around to, if you take an average, it may come around to 90 or 85 in that, which may not be sufficient. BPN is usually accurate, but when you go for giving a data with less number of tumor pixels, it will be very, very difficult for any human being or even network to identify. If you look at mild stage result, the efficiency is only 43%. Same way you go for real-time images, and the time period is huge. Sometimes BPN runs for 1 day. When I was a student, I used to switch on the computer and say, don't disturb, and I'll come home, right? Next day, when I go and check, I won't get the result. The power would have gone. And again, I have to rerun all the programs again. But now we have many parallel computing facilities, which would have made it much more easier. But BPN is relatively always slow, right? So my point is, how can I attack the computational complexity of BPN? SOM is less accurate, so I am attacking the accuracy portion of my SOM. BPN is computationally complex or it takes more time. How can I minimize that, right, without compromising the accuracy? So I'm going to make some modifications in the architecture and in the training algorithm. Look at the architecture. What modifications? Can you see any difference between this diagram and our BPN diagram? You can see that dotted lines target, right? Target is given both in the output layer and in the hidden layer, which is not done conventionally. Conventional BPN has output only in the output layer. Now I'm going to give it to the hidden layer also. Because I'm going to give it to the hidden layer, I should not call this as hidden layer. but I can call only as middle layer. This is one change I have made. Next, we'll see what happens. Modifications in the training algorithm. In the training algorithm, normally I said that you need to proceed from the first stage to the last stage, calculate your error, and based on the error, you come back. I am going to fix my error value, right? I am going to fix my error value, and I'm going to come from the backside to find out my weights U and V. So procedural flow, weight estimation is first done for the hidden layer weights. This is another difference from BPN. BPN, what happens? When you come from the reverse side, you find the weights of the output layer first. Now you are going to find the output of the hidden layer first. Now we'll go into the algorithm. Very simple, right? So this is the algorithm or out-of-box thinking approach for your modified BPN. What is the formula for error? Error is equal to target minus output. Now I'm going to fix my error value, right? Error cannot be made equal to 0. I hope you will accept that. Efficiency of a person cannot be equal to 100%. If error is not equal to 0, then what should be its value? Even if I run the BPN program, I stop my error with 0.01. So why don't I fix that? Right? So once if I fix my error as 0.01, the equation becomes E is equal to 0.01 or target minus output is equal to 0.01. Right? Then from that, I can find out what is my ZJ. What is my ZJ? Which layer's weight I am going to calculate? I am going to calculate the weights of hidden layer. What is the output of hidden layer? ZJ. You can refer your BPN later. ZJ is the output of the hidden layer. YK is the output of the output layer, right? So from the output ZJ, I have the target TJ and I am going to minus it with 0.01. Right now, I have got an expression for ZJ. Do I know the target values? Yes, I know the target values. So it is very easy to find out ZJ. Once I find ZJ, you come from the reverse direction. I will show once. Look at step number 4, right? Now I have got ZJ. Now if I want to find Z in J, what I should do? I know ZJ. If I know the function F, then I can very well find out Z in J. Once if I find Z in J, I know already X, then what can I find out? U, which is what I am going to do it with the heavy iterations in my conventional method. So only 3 steps. From the error, you find ZJ. From ZJ, you find Z in J. From Z in J, you find U. Right? So what is the function? If you do not know the function, you will not be able to do. The function says, the activation function is used in our BPN is sigmoidal activation function. The formula for sigmoidal function is 1 by 1 plus e power minus input. Right? That you have to note down in your scribbling pad, where our input here corresponds to Z in J. Right? So Zj is equal to 1 by 1 plus e power minus Z in J. With Z in J or the net value, you can find Zj like this. So how can you find Z in J from this expression? If you want to remove the exponential part, you have to use logarithm, natural logarithm. So if you use ln of Zj by 1 minus Zj, where Zj values are already known, you can find Z in J. So once you find the net value Z in J, the expression is going to be Z in J is equal to summation of xi into ui. This equation is the first equation of the training algorithm of BPN. Now I am coming from the back side, and if I know Z in J, if I know xi, I am going to find u with a simple process. Right? This is possible only if I'm able to calculate my error value in the hidden layer. That's why I have given the target also to my hidden layer. If I have my target in the hidden layer, that error calculation is possible, that Zj output is possible, that Zj net value is possible. From the net, my weight matrix can be estimated. Same way, how will you proceed with the output layer estimation of weights? Same formula. Here the formula is Tk minus Yk, where Yk is the output of the output layer. Zj is the output of the hidden layer. So from the same formula, Yk, you can find out Ynk, the net value of the output layer. And the formula says Ynk is equal to Zj into Vjk. So if you know Ynk, Zj, you know from the previous stage. Now it is very easy to find out Vjk. So you can find U and V with a simple mathematic calculation instead of going for iterative procedures. And when you look at the results, interestingly, the results seems to be better, right? When you look at F, right? Look at the F image. The previous F image is much more gaudy. But when you look at the F image now, it is not exactly correct, but still it is sufficiently better. Same thing I experimented with my real-time images also. Real-time images always gives you a better result because the tumor portion will be huge, right? Taking a huge portion of tumor portion is easy than going for finding the smaller portion of tumor pixels. If you look at my efficiency or accuracy, it has improved maybe somewhere around 95%, you can say. So these are the results you can check later. And interestingly, there is no iterations and my time period is reduced. Accuracy wise, both may be almost similar. If not, MBPN may be slightly better, but it is in the terms of convergence rate that my modified approach is going to overcome the conventional. Understood? SOM suffers from accuracy. So I found a solution for improving the accuracy. BPN suffers from slowness or low speed. So I found a method for improving the speed. At the same time, the other parameters should not be compromised. So this is the last one, conclusion and future scope. You must be knowing optimal methods for classification and segmentation. We can make use of ANN. And the future work is what I want to give to you. Different modifications can be framed for performance enhancements, right? You can have different modifications, different set of features you can use. You can think out of box in a different way, how we can go for enhancing the uh, performance of the system, and more different category images may be used. So that's what I want to say. And I want to give you this code, which I will try to take another 5 minutes or 10 minutes to explain this. This is based on a MATLAB software. You can take this code and go to your hostels or rooms, wherever you are. You can have a system with the MATLAB and check with that. Definitely you will get good results. But try to understand something because the code is very difficult to explain. So the first line CLC clear all, close all is the mandatory procedure for any MATLAB step. And now the first process in giving a program is giving the inputs and the targets, right? Now, can you see what is this X corresponds to, or can you say what is this X corresponds to? XOR function, XOR gate, right? 0, 0 means 0. 1, 1 means 0. 0, 1, 1. 1, 0 is 1, right? So here I have how many outputs? 4 outputs. Each set has 2 data, right? Because I have 4 outputs, I have 4 targets. My first target is 1, 1. You take the first value of X and the fifth value of X. These are called as one set. When it's separated by semicolon, it is called as it will come to the next line. That is called as one set. 1, 1 is 0. Next, you take the second value of X and the sixth value. 1, 0 is 1. 0, 1 is 1. 0, 0 is 0. Next, I want to initialize the weights. Initially, how will you weight? Will you initialize the weights? You will go for the random procedure. We make use of the command called as rand. Rand of 2, 4. Rand of 4, 4. Can you guess the architecture from these values? V is the weights between input layer and hidden layer. W is the weight between hidden layer and output layer. So if V is 2 comma 4, that means I have two input neurons. X has two data, right? One is 0. That one corresponds to one set of input. That's why I have 2 comma 4 as weight matrix for V. That means my hidden layer neurons have 4. So 2, 4, 4 is my architecture. 4 output classes. Each time I will give 2 inputs and 4 hidden neurons. And alpha learning rate, somebody asked, why should not be 0? It should not be 0, but you can have any value. Zero point 0.4 or zero point 0.3 is will give good results. Now I am going to show you how we are going to find the net value for your hidden layer. Z in J corresponds to the net value. What is the formula? Same formula. X into V. I have multiplied and find Z in J. From Z in J, what I should do? I should find Zj. What's the formula for a sigmoidal function? 1 by 1 plus e power minus input or Z in J. So I can find Zj. With Zj, this Zj will act as input for my next layer. I'm talking about the conventional BPN. Right? This Zj is the input for my next layer. So that layer's net value is Yin is equal to Z into W. And from that net value, I can calculate Y of I, which is my output of my output. Simple mathematical steps. So now we go for calculating my error. My error is T minus Y. And you look at the third step. I'm going to adjust my first weights. W is equal to W plus del W. What is that incremental weight? You would have remembered the formula. Alpha into, on the other side, input. What is the input for my output layer? Z. Previous layer's output is the input for my current layer. And I have del K. You go to one step above. Del K is equal to target minus output into differentiation of that net value. Right? You just compare this code with the BPN algorithm, you will find it as ditto. There will not be any change. Similarly, you go for adjusting the weights. V is equal to V plus del V. What is del V? For finding del V, you have to same formula, alpha into input. Now this is for the hidden layer weight. So what will be the input? X. And you have del J instead of del K. Now what is del J? Del J will have del in J, where del in J will have del K. This step is very, very, very important, right? Del K is the place where you have the error value. But here your error value is not directly related. Del K is present in del in J. Del in J is there in del J. Right? You will need time for this code to be understood by you. Have your algorithm side. Now have your code also. Change only the application, your application's input. You will get very good results. Right? Now I display all the values and I have my V and W. V corresponds to the weights and W corresponds to the weights. Here I have used, I think, 1000 iterations. Right? This is what I have used, 1000 iteration. But instead of iteration, you can also check whether your error value is 0 or not. That needs some extra programming, but this is one of the simplest skeleton I am giving so that you can understand it in a better way. So ultimately, at the end of the training process, you need a set of weights of V and W. Once if you have V and W, again go to the same conventional program, fix V, fix W, calculate net value, calculate um, your net value and then your output value of your hidden layer, calculate net value, output value of your output layer, and that will be your final output. If you have 4 output neurons, check which one is going to give you the maximum. For BPN, it is maximum. For SOM, it is minimum. So that's all for me to say. I think I have completed within the specific time, right? We can spend some more time for the question answer session, right? These are some of the concepts which you should know. Take time, go through it, then you can understand in a better way. Right? As usual, you are submitting the assignments in a neat manner. Assignment 3, write the implementation procedure of any two applications of ANN in your own words. Right? For these, you need to have the help of research papers. Right now, we are coming to the third day of FDP. I am having an understand that you are completely good in basics. So now we need to move to the expert criteria where we need to read some research papers. Check, at least download and check how neural network is used for their application. Write in your own words and submit any two applications. Thank you very much for your patient listening. Now we can have the question answer session. You can ask questions to me.
Shall I ask, sir?
Yes, sure, ma'am.
What is the difference between perceptron training and back propagation?
Perceptron training, even though we call it as a supervised methodology, right? There is no concept of error involved in that, right? Your perceptron is a single layer network. Your BPN is a multi-layer network. BPN works on stochastic gradient descent method, which I taught you in the previous session. But perceptron, they doesn't have anything. If you look at the incremental weight position of perceptron, it will be just alpha into x into t. It is only based on target. Only if you have a phenomenon called as t minus y, then we can find out error and the process will be better, right? So even though both are supervised because they have targets, BPN is going to be better than your perceptron in terms of your accuracy.
And the second one is what do you mean by kurtosis?
Kurtosis is a mathematical term, right? It is like the, what to say, where the data is clustered, right? Where the most of the data is grouped. When we say tumor portion within an metastasis image, tumor portion may be available in one place, or sometimes it may be available in other place also, right? Glioma or metastasis, they have the habit of having tumor in different portions, which is very, very difficult. When meningioma, on the other hand, they have a habit of having the tumor portion in the same place. So kurtosis checks or find out all the possible tumor portions in the form of a number, right? It comes under the mathematical statistical approach. If you want further details, you can refer any statistical textbook.
And the next one is how the noise appear in an image.
Um, Depending upon the image, you will have noises, right? You take a normal selfie, right? Everybody will take selfie. When you take a selfie, your hand will shake. When your hands shake, the illumination will change, the position will change. Our picture will remain the same, right? But there will be more lighting or different types of unwanted things may come into your image. That will affect the quality of the image. So noise appears in an image when there is a unwanted things are there in the image.
Hello, sir. Hello. Participants, please post your question in your chat box. I think sir connection is lost. He will come again. Hello.
Sorry, madam, there is some unstable internet connection on my side. Sorry very much.
And, next question. Sir said he checked with the doctor's result image. Is the result generated by any other AI methods? How to know the compared results are correct? How to select features?
No, if you want to check whether your compared results are correct, you need to again take your images to the doctors. There's no other way. The doctors are the only person who can clarify, check, and tell you whether it is correct or not. Right? Selection of features. It is again an open research problem. right? Based on literature survey, you can say that if people are using these type of features for MR brain images, then you can also make use of that because it's their past experience which say that it is giving the good result, right? Nowadays we have moment based features, right? Geometrical shape based features. Those features will give better results than only going for statistical features. Even you can mix two or three type of features, that will be always better. But I will advise you, you go to the literature survey for your specific application. I do not know what is your specific application. Thanks, Jamuna. I do not know what is your specific application, but you can search in the literature.
Uh, Next one is will a detection of disease or any object from images with any existing or a modified deep learning algorithm sufficient for a PhD research?
I think so because I have completed my thesis was completely based on modified approaches. Right, the thesis in the thesis they expect some contribution from your side. Right, what is your contribution? If you can develop some modified approaches, or there is also another option called as hybrid approaches, mixing two neural networks. That's very, very difficult, right? If you do something, say for example, 4 or 5 methods, 6 or 7 methods, then that should be sufficient for your thesis. That's what I understand. Instead of going for making use of the same existing methods and putting in your application, that is not going to be useful. How much you are contributing to the society in terms of research is very, very important. So yes, I think so.
Sir, DICOM images are visible only in MATLAB. Why we are unable to open it?
And DICOM images will have text, right? When you take an CT image of DICOM, you will have the patient's name, the age, all the data will be there. If you whenever you have such data, it is going to be a serious problem when you go for classification or segmentation. So I will advise you, you should not use DICOM images, right? Unless otherwise you go for image compression. If you go for image compression, DICOM is an uncompressed image, you can go make use of that, fine. But when you go for classification or disease detection, try to convert your DICOM image into some other format. Then you process on that, right? When you convert that, all the unwanted information will not be there. That will be much more better in giving a better support to the artificial neural network based system. Nowadays, I feel you can get images in variety of ways. You can ask the technician or the radiologist who is supporting you.
Next one is implementing deep learning in MATLAB or Python. Which one is the good choice?
Python. I can say 100% sure answer. It is going to be Python. I have experienced in MATLAB and also Python, right? MATLAB takes lots and lots of time. And if you increase the number of layers, it gets stuck. Then all my information will be lost. Again, I have to reboot. Unless otherwise, you are rich enough to have a costly computer, right? Python, it shows much data in a single line, right? So I feel Python is much more simple when you go for deep learning. But for artificial neural networks, it is sufficient to make use of MATLAB.
Next one is what is the percentage of data used for training, testing, and validation?
Excellent question. First, if you are starting, there is no necessity for validation. Right? People will ask you double-edged question. That means if you have 90% of training and 10% of testing, then immediately they will ask, how will you test your method with only 10% of images? Wrong. Then you will do 10% of training and 90% of testing. Then again, they will come and ask, you have trained your method only with 10% of images. Again, you are wrong, right? So to avoid that criteria, you can go for 60-40, 50-50. If you separate that into that percentage, it is going to be very good. Again, you have to keep in mind that it is not the percentage, it is the number of images. If you say my 90% image is only 4, then that is wrong. By default, it is going to be wrong, right? So when you say percentage, have for 60-40 or something like that, so you can answer both the questions. But the number of images in that percentage also should be very, very high.
Next question, sir. Sir, I'm a beginner. I'm interested to learn more. Interested to learn more. Please suggest me any textbook for gaining some more information or any other
Learning
source.
Lauren Fawcett. Laurene. I will repeat once again. Laurene. Lauren Fawcett. Faussett. Faussett. Fundamentals of Artificial Neural Networks. An excellent book. In fact, she is a lady. She is a lady and she has written an excellent book on the fundamental concepts of neural networks. If you study from the first page till the last page, you can give a webinar. Absolutely no doubt in that.
Next one is pre-processing required for images taken from the standard dataset?
Not necessary, right? Not necessary, because whenever any university uploaded data for the usage of research community, mostly they eliminate all the images and they place only the readily to be processed images. So it may not be necessary, but again, it depends upon your application.
Okay, next. Writing a paper for journal, can we replace ANN as just deep learning by word?
I did not understand. Can you
Hello.
repeat once again? Yes, madam. Can you repeat once again?
Okay, sir.
Paper for journal.
Writing a paper. Writing a paper for journal, can we replace ANN
Hmm.
just as deep learning by word?
I understand that if you are writing the text, you cannot write artificial neural networks as deep learning. The algorithm is different from of deep learning is different from artificial neural networks, right? So when you are typing the text in your research paper, ANN should be ANN, right? Deep learning should be deep learning. You cannot replace that. That is wrong. If you write deep learning, then my expectation will be different. So if possible,
Hello,
you
sir.
can come into the StreamYard also, because the questions of some of yours is slightly vague. So that if you can ask directly, I can give a better answer, I guess. Okay, madam, continue.
Hello, sir.
Yes, yes, madam.
Okay. Which deep learning algorithm? Which deep learning algorithm or technique is useful for increasing the performance in weather prediction?
Weather prediction. I have not worked in weather prediction, but I want to know what is the nature of your data for weather prediction, right? The data can be an image, or is it a signal, or is it a text, or is it in the form of a number? If it is in the form of an image, convolution neural network is the best option, right? That is the one which you have to test before going into testing generative adversarial networks, autoencoders, and other things, right? But now MATLAB has inbuilt commands for executing any data with numerical values also. Emotion recognition, I am doing on an application where we collect the data of phases of stress, anger, happy, and all those things. Those data are available in the form of numbers. But we have inbuilt setup in MATLAB for 2019, I think, for deep learning, where you can just drag and drop in that numerical data processing is also possible. But I will advise you first test with convolution neural networks, which is going to give you the best result. CNN in for deep learning is like BPN for artificial neural networks. So once you check that, then you can go for generative adversarial networks, GAN, autoencoders, LSTM. So many types are available.
Next one is what algorithm is used for multi-layer perceptron for classification?
What algorithm is used
Used
for
for multi-layer perceptron for classification.
multi-layer perceptron is nothing but back propagation neural network. Perceptron with a single layer is called as perceptron. But when you increase, because they found some drawbacks with perceptron, they increased one more layer in the perceptron and they called as multi-layer perceptron. Right? Multi-layer perceptron is backpropagation. That means you are going to make use of your gradient descent algorithm for your. The entire algorithm is called as gradient descent.
Hello.
Yeah, yes, madam.
That's all, sir.
Okay.
Sir. Sir, thank you so much for your inspiring and enlightening lecture. Really, I'm speechless after hearing your lecture, and I didn't, and I expect the same from the participants. Sir, we are very thirsty to listen to your lecture tomorrow. Once again, I thank you, sir,
Yeah,
for being with us.
thank you, participants. So today's session, try to think differently, right? Try to think differently. Only then your research papers will be accepted, your thesis will be accepted, and you can develop in your career. If you keep on taking only the things which are already available or made by someone else, that may not be called as a research contribution. For that, we need a good understanding of that. Thank you very much. We will meet tomorrow. Goodbye.
Bye, sir. Participants, thank you for your cooperation and energetic participation. We will meet you tomorrow. I think sir is in our FDP WhatsApp group. If you have any queries, you can ask in that group. Thank you. See you tomorrow.